This is the Flip-Flops 3 video, which is the first installment of the clocked RS flip-flop. Let's first examine the truth table and the logic symbol for a clocked RS flip-flop. On the right we have our logic symbol, and you should notice a couple of things are different when you compare this one to the RS flip-flop symbol. First, you should see this additional input, which is the clock, which, if you think about it, this clock now input means that we're dealing with a synchronous flip-flop. And that synchronous flip-flop is a really important concept because it means that those outputs that we're referring to in Q and Q naught will only change on the clock pulse. And we'll see when we look at the waveforms in the next slide how that works and why that is important. The other thing you should notice is there are no inverted inputs. So S doesn't have a circle there, a hollow circle or an inverter, neither does R. And what that means is it actually creates a nice, easy, simple, intuitive looking truth table on the left here. So let's look at that now. The only change you should really see with this truth table in the column here is this addition to the clock. But the rest is set up at the top, at least, the exact same as the RS. So you've got the mode of operations on the left, you've got the inputs, which are the S and the R, the Q and the Q naught, which are your outputs, and then the effect on Q output is on the far right there. Let's look carefully here at maybe the set state. We'll start with that one. And this clock pulse has to happen, and that's why it's there. It has to happen on the rising edge in this case. And you'll notice that this S is 1 and R is 0 for the set state. And remember that when we're in the set state, it means that Q is set to 1 as it's indicated here. And obviously the complement to that, Q naught, is 0. Well, that makes a lot more sense, I believe, if you think about it, to have S as 1 to initiate the set state. The previous flip-flop with the RS flip-flop meant it was a 0-1 input, meaning S was 0 to create the set state. And that's just not very intuitive. So the nice thing about these inverters not being there is that we create these situations which actually make sense intuitively. S is 1, we're in the set state. R is 1, we're in the reset state. And 0, 0 is the hold. And then we have the prohibited state at 1, 1, which we never use because that results in Q and Q naught both being 1, which obviously doesn't make any sense. This is the waveform for the clocked RS, and right away at the top you should see the added pulse train here with this clock that's generated. Again, going back to what we talked about earlier with the RS waveform, we have a clock pulse. One clock pulse is represented by a rising edge and a falling edge. So this time period here that it takes for this pulse to stay off at 0 at some time, and then it goes immediately from 0 to 1, and that's the rising edge. And then it stays on for some time, and then it has the falling edge where it goes from 1 to 0. And that represents that one clock cycle. And then it repeats itself over and over again, right? And we're assuming that it looks to be, just by looking at this clock pulse, that it's the same period, each of these pulses. So 1, 2 cycles, 3 clock cycles, 4, and then 5 and a little bit at the end. We have our regular inputs, S and R, and then we have Q. Because this is a clocked RS, we need to understand that the output Q will only change on a clock pulse. So rather than putting these dotted lines at changes in inputs, we're putting them at the clock pulses. Now specifically, we're putting them at the rising edge, or what we refer to as the positively edge trigger. You can have flip-flops that initiate an output change on the negative or the falling edge, but we're going to assume that with this flip-flop, it's a positively edge-triggered flip-flop, so that occurs on that rising edge. So we're going to do our dotted lines for all of these clock pulses, these 5. We're also going to remember that with these clocked RS flip-flops, or any clocked or synchronous flip-flop, that outputs never change in between these clock pulses. So if you look right here, you notice these inputs are changing. Well, that's not going to affect anything until we look here at this moment and understand what is being input, because it's right when the clock pulse goes from 0 to 1. So in between, just right here where I'm circling, is irrelevant. Unlike with the RS flip-flops, which is asynchronous, the output changes right when the input changes. This is not the case. We only change the output at the clock pulse. So let's look at this example we have here. S is 0 and R is 1. Well, we know that is the reset state, so Q starts as 0. But right at this moment, where it ends here, you'll see that S goes to 1, R goes to 0. What state is that in a clocked RS flip-flop? Well, we're right on the edge of this positively edge-triggered flip-flop when it's going 0 to 1. So right at that moment, everything happens at the same time. We actually are in the set state. And because we don't look at any more changes, and nothing's going to be affected in that output until the next clock pulse, we can simply draw this as being in the set state right to the end until we check it again here. So even if something did change here, it wouldn't affect Q at all. So the next clock pulse on the positive edge, we look here, we got S as 1, R as 0. So we're still where? We're still in the set state. Now right after that, you notice how this goes back to 0 and R goes up to 1. As I said earlier, this has no impact whatsoever on the output because we have to wait for the clock pulse. So we know at least it's going to stay set until the next clock pulse. Now, at this moment, yes, S is 0, R is 1. We're in the reset state, so it goes down to 0. And again, we have another change here where this actually goes down to 0, which would have created a hold state anyway, but the flip-flop would have ignored that because we have to only check at that rising edge. That rising edge, S goes to 1, R goes to 0, so we're back to the set state. And then it carries on through right to the end, as you see here, because no changes have occurred. And that's how you create the waveforms for the clocked RS. And that ends our video.